story time moment here. Brown dwarfs have been studied in earnest observationally since about 1995. That's the first time that Gliese 229b was looked at as a bona fide T-type object. And after that, you had a pile-up with the 2-micron all-sky survey coming on. A lot of brown dwarfs were identified. So at first, it was great, finding lots and lots of the L's and the T's. And as they were found, bunches of them started to pop up as looking weird. And they were kind of noted in the literature but tossed aside as like, that one looks a little bit strange. Why they look strange becomes very important. And in many ways, the outliers of any population end up informing you about your overall population by leaps and bounds. And so that's where I came in kind of picking up on a bunch of the outliers to say, okay, what's the deal with these? And I'll explain what they were now. So here's a common way we look at the brown dwarf population. This is a spectral type, and you'll notice I'm going to be focused on the L types for a lot of this talk, because almost every single directly imaged exoplanet, with the exception of maybe one, falls as an L-type object. That may very well change, but for right now, it's the L types that we all have to care about. On the y-axis here is the near to mid-infrared color, so the 2 mass J minus the Y is W2. And what I show you here is the trend of the colors for the distribution by spectral type. And what was noted was that you have this normal in the gray boxes with the black dots being the median. And then there was this spread with objects that were redward of that and blueward of that. And one of the things that I noted, and several others have noted now, is that when I isolated off the red types, I found that in a kinematic population analysis, I found that they were kinematically younger than the overall population. And the blue ones showed the opposite. The blue ones looked kinematically older than the mean of the population. Now, then going back and matching that with the oddballs that were being tossed and thrown as like spectrally these look weird, became the sample that I've been focused on. This sample of L dwarfs with spectral features that were anomalous. They turned out to be red. And it turns out that their spectral anomalies can be associated with low surface gravity features, hence a younger population of brown dwarfs. Here's what they looked like spectrally. This is average templates at each L spectral subtype from L0 down to L5 here. This is normal, and then this was the low gravity sequence. So when you look at this, you might say, oh, it look pretty similar to me. But I look at L dwarfs so much that when I see the red ones plop down, I'm like, holy moly, we got some outliers here. And I can highlight for you how you pull out those differences. The main one is at H-band. H-band shows a really triangular shape here, very different. This elbow is almost gone, that you usually see at about 1.6 microns. Then if you look zoom in on the vanadium oxide line, or absorption feature, you see it's deeper, bollier for the lower gravity objects. Potassium lines, shallower, narrower. All of these are signatures of a low surface gravity. Now at this point, we have two methods for designating what low gravity features we're seeing. And the jargon that you'll need for the rest of the talk, as defined here, is that we can take all of the spectra, line them up, and come up with two categories. There's the normal objects that would be the black lines in here. Then we've got the extremes, which we've called very low gravity, very low surface gravity, or the gammas. And then in between normal and very low gravity, there's an intermediate stage, which we call intermediate gravity, or beta. So you'll hear me refer to gammas or betas, and the hope was that, all right, we got this. We've got gammas as very low surface gravity, so they must be the youngest. And then we've got betas in between, so they must be intermediary. But the spoiler alert is that is going to fall apart when I start age calibrating this sample. All right, so how do I age calibrate it? Well, the one thing that I worked on, as I said, I grabbed onto the outlier population and I started going after measuring fundamental parameters, because that's the best way that you can figure out what's going on with the population. So in 2006, I initiated the Brown Dwarf Kinematics Project, the BDKP, and we've had multiple programs going on: radial velocity program, parallax program, proper motion program. The goal was to measure parallaxes for all brown dwarfs within 20 parsecs, to do a number of things, but also to include a select sample of scientifically interesting sources that we thought we could do great things with. One of which is the main sample I'm telling you about today, are these low surface gravity young ones. And so why would you do that? Here's a 3D simulation that was made for me by Adric Riedel, who's a postdoc in our group at the BDNYC. And this is flying you around UVW velocity space in the nearby vicinity of the sun. And we zoom in and around the collections of stars, young stars that are near the sun. So these are color-coded. These stars are all over the place. It's not like they're clumping. You're not seeing clustering of these objects for the most part. They cover some of which, AB Dor is all over the sky in the north and the south. Beta Pictoris, same thing. But in the nearby vicinity of the sun, you get these collections of stars that once you measure their full kinematics, you're able to say that they're moving with each other. And we've been able to go after the higher mass stars in these groups in order to age calibrate them. A few of us in this room were at a meeting last week, the Young Stars and Planets Near the Sun group, where there were some arguments as to the exact ages of some of these groups. So it's an ongoing question as to the ages, but no one denies that a lot of these groups are young, that are near the sun. So a couple of these that I'll show you here: TW Hydra, again, superstar, 2-mass 1207b, planetary mass companion. Then I'm showing you the groups and highlighting them for you by the exoplanet that's in them. So HR8799 system is in Columba, Beta Pictoris B is in Beta Pictoris. So each one of these groups has been the target of direct imaging campaigns, because these are the nearest, youngest stars to the sun. So of course, that's where we've been finding the planets. And now what we've done is, by taking that group of planets, or brown dwarfs, that showed the low surface gravity features, measuring their kinematics, essentially what I have uncovered is the siblings of the exoplanets, the ones that are in the same groups. So as I said, brown dwarfs are the key to understanding the exoplanets. And you could say just understanding regular brown dwarfs would help you. But the best thing that you could find is brown dwarfs that were younger as well, because then you could be doing a one-to-one comparison. So that is what we have uncovered at this point, the siblings of the exoplanets. And now I'm going to pull that group apart for you and show you how we are tearing into the fundamental parameters of all of these awesome objects in the groups. And the first place I'm going to start with that is in the parallax sample. So here's another little movie that I rendered for you, as if we were flying around 5 parsecs away from the sun or so. You can see the constellation lines are all distorted because we've moved away from the sun. We have at this point a little more than 300 late type M, L, T, and Y parallaxes through various programs, my own and several other people that have done amazing things with parallaxes. And even though Gaia is going to save the world and give us as many parallaxes as any of us has ever dreamed of, it will not get to the brown dwarfs. They're too faint for Gaia. So those people that do brown dwarf parallaxes are still in a job after Gaia comes out, because you still need to do those from the ground or maybe space-based missions. But let's take the brown dwarf parallax sample and pull it apart to pull out some trends here. And I'll start by showing you what's probably the most famous of all brown dwarf parallax diagrams that I can show you. And that's spectral type here. And I'm showing you everything right now, from M's all the way down to the Y's, and then absolute magnitude at J. And part of the reason why it's so famous is because of this totally bizarre thing that happens as you're getting to later spectral type, you're getting cooler, and then all of a sudden your flux, the amount of flux that you're getting changes, you get this bump. It's called the J-band bump. And that it happens when you go from L types to T types. That is a fascinating area of brown dwarf science, and it's worth a totally different colloquium. So I'm not going to focus on that one here. What I want you to focus on is the M to the L transition. And in this figure, I've pulled everything together by their spectral subtype. So if spectral subtype is a proxy for effective temperature, it should be including a lot of the things that go into changing your observable properties. But as you can see here, there's a lot of diversity in this figure. That diversity is driven by secondary parameters. Secondary parameters like, I can break that up for you because I know of some of these, binaries. So in this case, you've got a number of objects that you're getting 2 for the price of 1 in this figure, in that there's overluminous because there's 2 in there. There's subdwarfs, which are these older objects in this population. And then, the most important, are these young objects. So these young, low surface gravity objects that we're measuring the parallaxes for. And when this figure first started to come out, it was really boggling. Now I'm going to zoom in on it and show you exactly why that was. And now I'm going to start color coding it by the groups that I'm able to assign these objects to, and I'm going to pull them apart by the beta and the gamma designation. So let's zoom in on the M to the L's. And now I'm going to take you through band by band what we see for these objects. So this, now I've taken off normal objects and I've just fit a polynomial to it so that you are not distracted by those. All you're seeing here are the young type objects. And they're color-coded now by the groups that I've placed them in, A beta Radix, Tucanahorologium, Beta Pictoris, and then I'm showing you the symbols for the gammas and the betas, reminding you that the gammas were the very low gravity ones that we suspected as being the youngest, and the betas were intermediary. First thing to note that I can just pull out of this is that there's gammas and betas in groups of the same age. So we've got something wrong there, meaning that whatever the low surface gravity features are, you can see in Tucor, for instance, you've got both gammas and betas. Same thing in A beta Radix, the oldest group. If they're gray here, it means that they have low surface gravity features, but I can't place them in any group at this point. I don't know where they belong, but I do suspect that they're young. Second, and most important thing, is that something weird's happening where the young M dwarfs do something very different than the young L dwarfs. So that the young M dwarfs, I'm sticking with J-band at this first plot, they're overbright, whereas the young L dwarfs are what I call underbright. And let's see, this is only a J-band though. Now I'm going to take you through band by band how that changes. On the bottom here, I'm showing you the residuals from how different the objects are from normal, from what the mean of field objects is. So this little flip through will go through band by band, J, H, K, and then, so the 2 mass magnitudes, W1, W2, and then W3. Whenever I get to W3, I get so excited I can't wait to see what's going to happen at W4, but none of the brown dwarfs are bright enough to see in W4, so we don't have that data yet. But what you're watching is essentially a flux redistribution, so that especially if you see the L-type objects, which were boggling us at J-band, by the time they get to W3, it's different. They're above the sequence. So now I'm going to dive into what that whole spectral energy distribution might look like. But this was a fantastic sign for flux redistribution, especially for the late-type L dwarfs, the young late-type Ls. So what we've been doing is the best way to go at this is to fill in a complete spectral energy distribution for the parallax sample. So our team has been pulling together parallaxes from wherever we could get them, numerous groups with their parallaxes, so all of the parallaxes, and then collecting all the photometry, all of the spectra, whatever you can give me, I will take and I will include it in trying to construct one of these, what I think are some beautiful empirical spectral energy distributions. They come from 25 different instruments. Here's an example of one. And I want to highlight that a lot of this, we've written a Python database to hold all of this. And a grad student I work with, Joe Filipazzo, who's at CUNY CSI, has been doing a lot of this work. You can see we filled in the spectral energy distribution with catalog photometry, SDSS, DSS, 2MASS, WISE, Spitzer if it had it, and then all of the spectra we could find from whatever instrument you could give us in order to create these beautiful spectral energy distributions. And I'm just going to give you a little bit of spectral energy distribution eye candy by showing you a whole bunch of the ones that we have. So we call this the BDNYC Spectral Energy Distribution Library. At this point, our tally is we're collecting anything that's M6 to T8 with a parallax. We have 172 objects in total, 46 of which are young. So these now are going to be my ability to compare what a young L-type looks like to a normal L-type by just the empirical data calibrated with the parallax. So here's an example of one. Two L-type objects. One is this L4 gamma. So gamma, again, was the very low gravity objects. And then a normal L4. And what these two objects have in common is that they're typed the same way. They're both L4s. They're both, and they both have a very similar bolometric luminosity. Because the best thing I can do with this database of spectral energy distributions is then integrate under the curve and tell you what the bolometric luminosity is empirically. No bolometric corrections required. And what we find is that when you look at the two SEDs next to each other, the young object is indeed, it's under bright when you compare 1-to-1 to the L4. And somewhere in the near infrared, that flux shifts until you get into the mid-infrared where the object switches to being over bright. And this is awesome. I'm so excited that we're finally able to show it like this. And what it is this direct evidence that these young L-type objects, they're dustier. One of the things that can shift that flux to longer wavelengths is a dustier photosphere, or they have higher lying clouds. I'll say that those two things are hard to distinguish between each other. But grad student Kei Hironaka, who's working with us at the BDNYC, she has been working on figuring out how to fit extinction laws to this differences in SEDs to say something about the grain properties of the clouds that might be dominant in these kinds of objects. And a little bit more evidence as to the dust in these objects is if I zoom in the mid-infrared spectrum on one object that is my absolute favorite of all the young brown dwarfs. And you're not supposed to have favorites when it comes to children, and these are sort of children, but this is my favorite. So 2MASS 0355, I did a detailed study on it in 2013, and this is a mid-infrared spectrum that we haven't published yet, and what it shows when I compare it to a normal L5 is this whopping silicon grains absorption feature. You do not see that in a normal L5, you see it in this L5, 2MASS 0355. And I want to just show you why I love 2MASS 0355 so much. Again, I'm showing 2MASS 1207b, again, that a beautiful, gorgeous, directly imaged exoplanet. And I can compare 2MASS 0355, which is the black line in here, to a normal, this is just a normal generic L5 object. And then you can compare it to 2MASS 1207b. And when I saw this at first, I was blown away. It looks so much like it. So much like it. The sharply peaked H band here, the fit through J band, the potassium line, the iron hydride line, CO even, or there's differences in the J band, which I think is a temperature difference between the two of them because they are slightly different temperatures. But the CO is even very similar. But herein lies the wrench in all of this, is that, yeah, it's a lot like it. But 2MASS 1207b is in TW Hydra. It's 10 million years old. 2MASS 0355 is in AB Doradus, and that is 150 million years old. That's a big difference in age for these two objects. This plot is also kind of summarizing what still is a beautiful confusion that we have, spectral type versus the J minus W2, and showing you how the age distribution, meaning the oldest AB doratus in orange here, to the youngest TW hydra, and gammas and betas, they're all over the place. And the one thing to think about that I focus on a lot with 2MASS 0355 is that younger doesn't mean dustier. There's other things that are driving what's going on. And I'll show you one of the other amazing things that comes out of this, back to the parallax sample. So back to those beautiful SEDs, and maybe what's helped us understand what might be causing some of these problems, is that I focus again on my spectral energy distribution sample. And as I said, one of the things that I can do is measure bolometric luminosities from those empirical bolometric luminosities. So we've gone ahead and done that, redone anything that had a parallax in a uniform way. This is the full brown dwarf spectral type from late type M all the way to Y type bolometric luminosity. Again, this is a paper that's been led by Joe Filipazzo, who's a grad student in our group. And from M into T to Y, you can see how regular bolometric luminosity goes. Now, if you look at what the young objects do, I can switch and see that. And what we have here is the young M dwarfs do what you suspect they should be doing. They're overluminous. This is classic of young things, right? They haven't contracted to their final radius yet. You expect them to be overluminous. But the L dwarfs, they don't do that. They are much more normal. We don't have enough T types in order to say for sure. So what does that mean? That's weird. What does that mean? Well, you can then look from bolometric luminosity to an effective temperature. And unfortunately, in order to do that, I, for the first time, would say we have to turn to the evolutionary models. So the radii come from evolutionary models at this point, because we don't have direct brown dwarf radii. And really, there's 2, maybe 3, that we can actually turn to for help here. But for the most part, we have to turn to the evolutionary models for help. This is what the effective temperature relationships look for brown dwarfs. And now on to what the young objects look like. What you see is this very interesting, bizarre effect that the effective temperature of low gravity L-type objects directly applicable to your favorite directly imaged exoplanet are up to 300 degrees Kelvin cooler than an equivalent older object. So they're cooler than you would have expected them to be. A problematic result in some ways, because the effective temperature, again, is how we're trying to understand exactly what's going on with these objects. Let me put this in context with the exoplanets for you. Another extremely famous figure that you'll see in any directly imaged exoplanet paper, and that's the near-infrared color magnitude diagram, J minus K versus the absolute magnitude in J. And what this is populated with here is the M dwarfs into the L dwarfs, and then over into the T dwarfs, and then highlighted for you on the right-hand side in this sequence are the collection of directly imaged exoplanets labeled here, as well as the young brown dwarfs. Now, I'm going to change the colors up for you and show it to you age calibrated. So just guiding your eye, this is what our normal sequence down and then over. When you go from the L to T transition, this is where that J bump thing happened. This is largely an atmospheric effect. Color code them now by their groups. And what's interesting here, which is rather obvious, is that the sequence of the young objects are redward and under where you would expect them to be. And that I've been pointing it out then throughout a lot of my plots here as to why we think it is. Flux redistribution, probably driven by these dusty photospheres. color-coded now. So the youngest objects in here are some of these planetary mass companions that have been found in nearby star-forming regions, so less than 5 million years. They certainly look like they pushed the trend redward. Then, the more important thing to notice is when you get towards the bottom of this entire sequence, where we're just filling out with some of our young brown dwarfs. And what the idea was here is this turnover happens between L types and T types, where you get a cloud clearing, objects get cooler, and all of a sudden they start losing clouds because in that first cartoon diagram I showed you, methane gas starts to dominate. But as you get to younger and younger and later objects, 2-mass 1207b is the extreme of which what's happening is that transition where it goes from an L-type object to a T-type object seems to be happening at a later and later absolute magnitude. Or, in other words, it's happening at a later and later effective temperature, at a cooler effective temperature. The clouds are sticking around for longer. The clouds are problematic in all of your observable features. Okay, now I'm also going to put this in the context of the masses of these objects. This is now a bolometric luminosity, which we've nicely accumulated for a lot of objects from those beautiful SCDs, and the age of the object. And now I have labeled for you this collection of exoplanets, and the green objects on here are all of the young brown dwarf sample, and all the red lines are the same as the first plot I showed you, where this is planetary mass objects. So this line in here is a 10 Jupiter mass object. So you can see many of the directly imaged exoplanets are landing in here. And then these green triangles, which are the age-calibrated sample of brown dwarfs, they are creeping in to planetary mass. So at this point, we've not only found a collection of young brown dwarfs that you can use to compare to your favorite exoplanet to try and characterize its atmosphere, its clouds, its effective temperatures, but now they're also equivalents. But these objects are isolated. They don't have a parent star hanging out with them. They're alone. So that in its own right is a movement in our own studies to try and understand what the mass function is for these groups, what the mass function is at the end of maybe planetary star formation processes, or maybe it's the high end of planetary mass function.